Hari, you can start.
Yeah, thanks, Jason. Hi guys, good afternoon. Myself, Hari, working as a team developer in e-Yantra. So we can start the video. Yeah. Hi guys, myself, Hari. I'm working as a staff in e-Yantra and a team developer in previous year and a team developer for e-Commander bottom this year. So we would be starting a session in around 5 minutes. So ask your friends to join if they are not here.
Hari, you there?
Yeah. So I'll start 2-5.
It's fine. You can start.
Just 2 minutes. Yeah, I'll start. So yeah, like, I think why does we should get started, please get started with the session. So yeah, like good afternoon to all, and welcome to this particular session on FPGA. So let's get started with what is going to be covered on this particular session. So I hope I'm audible as well, and my screen is clear. So yeah, so agenda would be we would be covering what is an FPGA. We'll give you an intro and then detailed overview, and at the end, we will show you how exactly the FPGA works and everything. And then we will have a comparison between FPGA, ASIC, and a microcontroller. And then we will continue to understand what are the HDLs and then how to use them to basically visualize what you're trying to do. So yeah, going ahead, we would be seeing where FPGAs are getting used and what is the scope of FPGA and learning FPGAs. And then we would be understanding what is the design flow of FPGAs. Okay, so with that information, let's get started with that. So the very first thing, introduction to FPGA. But before understanding why FPGA, we might be interested in understanding why FPGA came into an existence and why FPGAs are being used. So to do understand that, I would be throwing you to a first question: what is an electronic design? How many of you can answer in the chat, or you can unmute and you can answer it? What is an electronic design, or at least from this image, what you can understand? Like, can you anyone can put me in a chat? Anyone from electronic students should be there. Even mechanical, anyone can answer it. It is from an image and two words, right? So yeah, who is the first one to break out the silence? Designing an electrical circuit. Yeah, anyone else want to answer? Okay, so as we said, designing an electrical circuit basically. So we are designing an electrical circuit, that's right, but that electrical circuit does what? So we need to understand the role of that particular circuit, right? So from the actual definitions, what is it saying is process of developing a circuit by using known electronic components in order to meet the given specification. Now we have two words highlighted, which is known and one is specifications. So these two words have two different meanings, and based on that, we are going to design a circuit, right? So let us understand what does it mean by known first, and then what it mean by what does it mean by specification first, and what does it mean by known second. Okay. So as the name specification says, let's go to the answer first. Good. As the name specification says, it is like I need to design a circuit, but what is the problem, right? So assume I wanted to design a circuit which will transmit some message from maybe say my tablet to my mobile. So that is my specification. Just abstracted specification. It might have a lot of details in that, but I'm telling I want to transmit some message, and to do that, I want to design a circuit. So how do I do that? So they said the specification, and I need to understand what are the components I can use to design that particular circuit. I'm telling the abstracted way. We will get into details at the later end. So specification is nothing but a problem statement to which you are trying to form a solution by designing a circuit, right? And then known devices in sense you are going to design a solution, but that particular solution will have lot of components involved. Maybe it can be a resistor, transistor, even some particular ICs also it can be. I hope everyone knows what is IC. IC is an integrated circuit which will perform some basic operations, right? So those are also there. So we are trying to build a solution by using the known devices for a given specification. This is called electronic design. And then life cycle of electronic products are nothing but so we started the design. We are given with a problem and we started with the design. And from that particular point till the end point, and then how long it can be used. This is known as life cycle of an electronic product. So I hope everyone can understand what it is meant by electronic design. And I'll go little beyond. So yeah, so if you can see from the image, right? So people are trying to like look at various chips available on the market, and then they are trying to design solution to a problem. Okay, so what do we call in terms of as an electrical engineer or an electronics engineer or whoever want to design an electronic design to solve a problem? What they will call it as, they will call it as process of converting a behavioral description of a circuit to a structural description. So what does it mean? Behavioral description is like, assume you know Python and you are writing a function. What is function? Function can be anything. Like if I write a function to find a minimum element, so what is my problem? Like what is the purpose of this function? I need to find the minimum of an array, right? Similarly, behavior is nothing but what does that particular electrical circuit is going to do. So we need to describe that behavior. So anyone has to say something? Okay, so yeah, I'll continue. So we know the behavior of the circuit or behavioral description, like we can define a behavioral description based on a problem statement, but that is not enough. We need to make sure that, just a minute. Yeah, we need to make sure that we are converting that particular behavioral description into a structural description. Structural descriptions are nothing but we are actually choosing a component, how to wire them, and how to make a circuit. So that's how like all the PCBs are also done, right? So similar thing. So yeah, that is electronic design, and like that is start of the electronic design. Can someone mute yourself? It is echoing from your. Okay, let me continue. So basically, yeah, as a part of your electronic design, you would be converting your behavioral description into a structural description.
ஏன்டா
Guys, Navneet, your mic is unmute. Navneet, your mic is unmute. You can mute.
ஒண்ணுடா உடனே சொன்னேன் ஏன் பண்ண?
Search his name and okay. Okay, let's continue. So yeah, I was speaking about electronic design and the process of conversion of behavioral description to a structural description is one part of electronic design. So after conversion, we need to physically do physical design, which is involving choosing a component with the proper sizes and then physical arrangement and then connections. Connections are nothing but how you are going to wire one component to the another component. So these things to be done, right? These things to be done, and then again you need to verify your behavioral description is working after your physical design. So a lot of these things are involved into electronical design, right? So yeah, but in FPGAs based, like we don't need to choose a component and then define an physical arrangement or even connect somewhere. So whatever you are trying to do as a behavioral description or whatever you are trying to solve, it is we need to define that in terms of an algorithm. And the FPGAs are smart enough, like basically your tools are smart enough to understand your FPGA and then design your physical design, and then we can directly use upon it. Okay. So we would be like I would be showing how this particular physical design is already done on the FPGA and why we don't need to worry about that in the later slides. But for now, the point to understand over here is what is the like traditional electronic design, how you are converting your problem statement into behavioral description, and how you are converting from behavioral description into structural, and then how you are going to do a physical design. So these are the process involved in electronic design, and we would be seeing how FPGA can help this particular process to make faster prototyping and like that. Okay, so yeah, let's continue with standard chips. So yeah, so if I assume I wanted to do any digital operation, we are mostly speaking about digital operations here. So if I want to use an digital IC, this 7400 series is a very famous series of ICs in which we have a NOT gate, AND gate, OR gate, and more other gates to implement, right? If your teacher asks you to implement maybe a full ladder, what you would do in your electronics lab or something, you would be connecting all the components physically, right, using this particular ICs. So these ICs are available in the market widely. But what are the drawbacks do you think it has? Can anyone say in the chat? What are the drawbacks it might have? So we have these particular standard chips, and this particular standard chips are defined like that. But what do you think as a drawback? Size. Okay, size is the drawback. Anything else? Yeah. So and then it has redundant space, like as you guys said, size is there. And then you can also see even in this particular chip or in any of this particular chips, only have defined inputs and defined outputs, right? So you can have four AND gates, and if you want to use more AND gates, you can't use. Power consumption is also a good point, right? But let's speak about more into a size and form factor and everything. So yeah, continuing with that. So we have defined number of inputs and outputs. If I want to use more AND gate, what I need to do? I need to have one more IC of the same type. But what if I don't want to use one? I want to use only one AND gate. So I have redundant AND gates available which are not going to be used, right? So these kind of problems occurs, right? So basically we don't have a extra, like we don't have an appropriate amount of gates to work on. So here comes, these are one of the drawbacks of using these particular standard chips. So we have some more points to add on those particular things. So yeah, also if you can see, if I choose one particular IC, that particular IC is very fixed to one particular functions, right? If you can see from the previous slide, it was very fixed to 7404 is very fixed to that particular operation. It is what? If you can guess, it is should be not gate, right? So it is not gate. So that is very fixed to that particular gate. So these kind of fixed behavior is not really general, right? If I want to apply like do some more operations or do some other functions, it is not possible. So that is also one of the reason why standard chips are not always the best choice. Okay. So yeah. So we are trying to, people who were designing electronic design in a like in a bigger companies was trying to do this, and they found out, no, this is not the right way to do it. We need something that can actually very generic, and I can usually prototype faster. Prototype faster in sense they wanted to make a circuit faster. Basically, that is called prototyping. So you are given with some problem, and then you are trying to form a solution, and they call it as prototyping a solution. And they wanted to do as fast as they can so that they can do verification, testing, and then everything, right? So these things were not possible or very time consuming and money consuming in terms of doing on standard ICs. That's why they are trying to form out new solutions, and we will be seeing what are those solutions they came up with and how FPGA came up into an existence. Okay. So yeah, so as I were discussing about, they came up with the first solution, like why don't I program this particular logic device? If you can see from the previous slide, all the standard chips I mentioned are logical devices, right? So those logical device, why can't I program it properly? Like why can't I say for this inputs and this much amount of space I need to program, and I can use it as as a solution. So they created a programmable logic device which will contain some amount of logic gates and programmable switches so that I can use only those particular switches and gates. So those came into existence before FPGAs. And then we have, yeah, as I said, like, so those communications or those connections are defined using switches. Those switches are also programmable. So we would be seeing how that is possible. So as a general structure, you can see this particular diagram on the right, which has lot of inputs and it has lot of outputs, but there are some logical gates and programmable switches. We call this particular block, like this particular block as programmable logic device block. So based on the inputs and whatever way we are trying to program, it will generate that particular output based on the logic function. So we will see what are those programmable logic devices. So the very first one is programmable logical array, PLA, or this is also called as SPLD. For some reason, it is not showing at the bottom line. It is written as SPLD. Okay, simple programmable logic device it is called as. And the first one is programmable logic array. So yeah, so let us take an example. So we have two functions. So x1, x2 plus x1, x3 bar plus x1 bar, x2 bar, and x3. First question is, can you anyone recognize what kind of expression it is? I hope everyone knows basics of digital electronics. What kind of expression it is? Can anyone say? SOP. Yeah. SOP is nothing but sum of products, right? So we have this particular Boolean function, which is expressed in terms of sum of products, and we have two of those. So how do I program it? If I in a traditional way, if I want to program or realize this particular Boolean function, what should I do? I need to have one AND gate, one one, two, three AND gate, and then some amount of NOT gates, and then I need to have OR gates, right? So these many ICs I need to use based on the size. So instead of that, we have this particular programmable logic array, in which it means we have one AND gate programmable, we have one AND plane, and we have one OR plane. Okay, so totally we have two programmable planes. What I would be defining is based on the inputs. If you can see here, x1, x2, x3 are inputs. So the first expression is x1 and x2. So we need to multiply x1 and x2, right? So if you can see this interprogrammable switch, it is all connected together, right? So if you can see here, x1, x2 is connected, and if you go through others, you can see this particular, all these particular values are being connected over this particular areas. And then if you can see over here, wherever I need to add, so these and this particular point I need to add, right? So those are also interconnected. By using that, I can realize function one. Similarly, if I by programming the switches, just by programming in the switches, I can realize function two. Where am I programming? If you can see, programmable connections are done just near the AND gate and just near the OR gate. So this is how it is called programmable logic array. You are able to realize a Boolean function by programming the switches, or we can also call it as interconnects to the gates and to realize a Boolean function, right? So this is one of the idea they came up with after realizing that standard ICs are not really best choice to design an electronic design. So they came up with this particular PLA. But again, this particular PLA is also very, constrained on number of gates they can use, number of inputs for a particular gate. If you can see, this particular AND gate is 6 input, but what if I need to have one more variable? Let's say I have four input variable, x1, x2, x3, x4. Then I need to increase the size of AND gate, size of OR gate, right? So these problem still was there. So they are trying to form one more solution, or they are trying to improvise what they can do. So again, they came up with one more idea, which is programmable logic array. Previous one was programmable array logic. Now it is programmable logic array. Sorry. Sorry. We are speaking about programmable logic array till now. We will go to PAL later. So yeah, similar to what I was telling previously, they realized this particular interconnects here and show them how this particular solution is being formed. Okay. So nothing more over here. Let's move to PAL now, programmable array logic. So this is also a simple programmable logic device, comes under simple programmable logic device. So programmable logic device has two classification. One is simple and another is complex. So in simple, we have PLA and PAL, and in complex, we will have, we'll go there before we jump into direction, jump into it. So we'll go one by one. So yeah, so here if you can see, we have two more set of Boolean functions. And then this particular Boolean functions is of which type? I hope, again, anyone can say which type it is? SOP, right. This is also of SOP. So here what we have is, we have fixed OR gates. So if you can see, we have fixed OR gates over here, and one programmable AND plane. And also again, we are trying to program the switcher. So we will define what are the connections to be made to realize these equations. So similar to the previous slide, it is also interconnecting x1, x2, and x3 bar, and to form an addition operation. And then similarly, will form an OR operation, similarly to the second function as well. So this is how it is different from PLA and PAL. PLA, you had both AND and OR gate to be programmable, but here you have only one plane, which is AND plane to programmable. So that is the difference between PAL and PLA. So based on the application, the difference is this, but the based on the application of the electronic design, people were choosing between PLA and PALs. So if they are designers more into different logics, they were preferring PLA, because you don't have an option over here, right? So that you can't program RGate, but there you are supposed to program RGate as well. So based on PL like applications, people are switching between PLA and PAL. Still, the same drawbacks applicable, right? That there are defined number of gates, and how do I improvise this? So then it comes the complex programmable logic device. So in complex programmable logic device, people were thinking, I have one PAL, and I have one PLA. How do I improvise it? They thought about this, and they come up with, why not I'll have something like PAL or PLA. I'm gonna try change. PAL or PLA, and then I have multiples of them and connect them together. So people come up with that particular idea, and they have lot of interconnects as well. And then those interconnections are nothing but how you connect input and output together with gates. That's what interconnectors are meant. And then they are trying to put many PIL and PLA like block together, and then make sure you have a programmable device which is little complex, but it is capable enough to program a generic device, like generic functions. So people came up with this idea, and yeah, so with this idea, but this idea is also, again, if you can see from the previous slide, this is also pretty limited in structure and pretty limited in genericity. What if I wanted to realize lots and lots of number of inputs, then you need to increase a lot and lot of, AND gate, OR gate, and everything. So people are still not satisfied with this particular solution. So people at the last came up with the solution FPGA. So let's look what is FPGA. So if you can see, I said we have an AND gate, OR gate, which are fixed, and the function of those are fixed. What if they can come up with a solution which you don't fix that particular block as an AND gate or OR gate? Basically, you would be having just a moment. So basically, you would be having a block. Let's assume I have a block and I pass A and B. Let's have like for a small assumption, we'll have only two inputs, and I will have and one output Y. I don't want to say this is an AND gate or gate or NOR gate, whatever gate it is. I don't want to say. I just want to say if I want AND gate, I wanted this particular block to be AND gate. If I want that to be an OR gate, I want that particular block to be an OR gate. I don't want to define a function. So what I can do, so people were thinking about it, and they came up with the solution called FPGA, or configurable logic blocks. If you can see over here, there is one particular small block, right? CLB, configurable logic block, we will call it as, and there are multiple of those, and there are multiple interconnects connecting between that. So one particular logic block has three different elements. One is LUT, we call it as let or lookup table, and we have one particular flip flop. I hope everyone knows why flip flop is used in a synchronous circuit. It is nothing but a memory element, and you have a multiplexer. Okay. So what this particular logic element does is, or what this particular how it is configurable. Let me come to that particular point first. So how it becomes configurable is, okay. So before that, let me say how it is. Like I said, right? I said right now, right? I wanted this particular block to be an AND gate, OR gate, anything, right, like that. But how it becomes configurable is this, using this particular LUT, and how it is doing is this particular diagram. I hope you can see this particular diagram, right? So this particular diagram, let's assume it is for AND gate. If it is for AND gate, so what, when the value of x2 and x3 and x1, x2, x3 to be, what should be the value of x1, x2, x3 so that the y value should be 1? Can anyone say? It is a 3-input AND gate. When what should be the value of x1, x2, x3? Yeah, it should be 1, 1, 1, right? To the value of y to be 1. Yeah. So how do we do that? So we have this particular lot of multiplexer inside it, and we pass x1, x2, and x3 as selection lines. I hope everyone knows how multiplexer works. So for a small example, if I want to say, let's have 2 cross 1 mux. So I'll draw something like this, and I have one particular line to select an input. So we have one particular value D0 and another one D1, and we have one selection line. If my selection line is 0, it will take output D0, or if my selection line is D1, it will take, sorry, selection line value is 1, it will take D1 instead of D0. So this is how a simple multiplexer works, right? So based on that, what I can do is I can define this particular configure logic block. And as I said, like as you guys said, the value of y should be 1 when x1, x2, x3 is 1, right? So that is nothing but, in configure logic block, it is an address. Okay. So each values are being stored with 0 or 1 over here. This is called LUT mask, LUT mask it is called. Whatever values here stored over here is called LUT mask. Okay. So what we need, so in the very last value, it should be 1. On address 111, which is 7, it should give me 1. So what it will do is, it will store 0. Like this particular configure logic block will store 0 on all those addresses, like from 0, 0 to 0, 0, 0 to it is what 6, right? 1, 1, 0. All the values till here is 0. So it will store 0 on this particular points, and at the end it will store 1. So for that, what should be the selection line? If you can see, x3 should be 1, right? x3 is 1. x3 is made 1. So it will choose a value of 1 over here, as I said before, and that is passed over here. And here, if it is what x2 is also 1, right? So x2 is 1. If you can see, if this is for 0. So it is 1 over here, it is 1 over here. So it will take this particular value 1. So here also it is 1. Here it will choose x1 is also 1. So x1 is also 1 instance, whatever value coming from this particular line will be chosen, which is 1. So this is how a configured logic block can be programmed to realize any function. If I want to use OR gate also, I can do the same. OR gate, if you remember, for 0, 0, 0 alone, it should be 0. For every other value, it should be 1. You can change this particular LUT mask. It is called LUT mask. LUT mask it is called. Okay. Changing this particular LUT mask and identifying what should be the input, and what should be the output, you can configure in any way. You can use it as AND or not, any gate. Okay. This is how, like, this particular configurable logic blocks are very helpful in developing this particular device called FPGA.
आपण ज्या व्यक्तीला कॉल केला आहे त्याने आपला कॉल
Someone
होल्डवर ठेवला आहे. कृपया लाईनवर राहा.
can mute himself, calling user. Okay, you are muted. Thanks. So yeah. So apart from it, just LUT, like if you can see, this particular configurable logic block has three things. One is LUT, which I explained right over here, LUTs, and then you have one particular flip flop. So it can store 1 bit register, 1 bit value, right? And then it can have a mux. So if you want to get the value of flip flop or from the value T LUT, you can use this particular mux to choose an output. Okay. Similarly, you have multiple number of blocks to realize any application. This is how it becomes very generic to use or design any particular electronic design for digital circuits. So yeah. So apart from it, if you can see, there are a lot of switching blocks. Switching blocks are nothing but, again, this is a programmable matrix. Like you can say which block is connected to which particular block. So that, like, this particular block I said for one AND gate, right? If I have multiple AND gates, you can define multiple AND gates, or you can define whatever you want, like anything. We will see whatever application we can design on this particular FPGAs. But for now, what to understand is what is CLB, and then what is switching block, and how LUT works. If anyone has a question on how these things work, you can ask. In short, I can repeat. One configurable logic block has three things. One is lookup tables or LUT. And if anyone asks what LUT is, how LUT is working, LUT is nothing but a lot of multiplexers within it, which has the LUT mask, which is defined to define a particular function of a digital device, and based on the multiplexer value or input values of to that particular lookup table, you can identify an output, and that particular output can be passed to the flip flop, or else you can use the value of LUT directly as an output from that configurable logic blocks. Hope it is making clear. Yeah, it is similar, but it is based on a very large scale. And if you are just using a similar, like just using a mux, it is not possible to store an element, right? So that's why they integrated with flip flops and SRAMs, and there are RAMs, right? RAMs to store the values of that register so that you can use it on later purposes. So yeah, it is, in short, it is similar, but in mux, you can realize the equations, some equations, but you will not be able to store a value, right? Here you can store a value because these FPGAs are loaded with some amount of embedded memory. So that's how, just using mux, you can realize equations, but you can't do more things. Switching block, yeah, sure. Switching blocks are nothing but, if you can see, we have implemented one particular, like we have configured one logic block to use it as an AND gate, right? So we are using this particular logic. Assumption is we are using this particular AND gate as, like, this particular configured logic block as AND gate. Then I need to pass this particular result to some other some other configured logic block. Let's say configured logic block 2, which is dependent on this particular output. what should I do? I should somehow connect this the output to output as an input to this particular block, right? How do I define that? That's why we are going to use switching block. If this is that particular configure logic block and my next logic block is over here, I need in some means I need to pass this particular output y to as an input over here, right? Then how would I do it? And I can also pass some other variables, maybe x2. If you can see from previous equation, it is depend y can be dependent on multiple variables, and multiple variables can be programmed on multiple CLBs. So how do I define those connections? That's why these particular switching blocks are being used. In FPGAs, this particular configurations are very open-minded, like open-minded in sense, very open to for us to see and explore. But the switching blocks are not open to see, like they will not be disclosing how this particular switching blocks are being synthesized. So in FPGA, we call it as like you pay for the like you work on the FPGA, like you work on the hardware, but programming this particular switches is where all the costs go. Like the cost of FPGA is for the better switching and everything. Okay, so yeah, let's go ahead with this. So yeah, so considering programmable logic stuff, let me give you a recap of what is digital logic is. We have a standard logic in which we have TTL and CMOS. I hope everyone knows what is TTL, digital family, and CMOS. And then we have programmable logic in which we have PLDs, simple PLDs and CPLDs, the simple programmable logic device and complex programmable logic device, and comes the FPGAs. And then apart from it, we have ASICs. Can anyone say what is ASIC? And ASICs is also, realized using two ways. One is gate array and standard cells. Anyone knows what is ASIC? Okay, ASICs are nothing but application-specific integrated circuits, right? So application-specific integrated circuit, as the name says, so you are designing one particular electronic design. Like as I said previously, we have one problem statement, and I am defining like creating one particular IC to solve that problem. That is an application-specific integrated circuit, right? So those are also there, and those are realized using gate arrays and standard cells. Apart from it, we have full custom designs which are microprocessor, RAM, like we have microcontrollers also, right? So those are full custom designs. So these are the programmable logic stuff we are using or we can see everywhere. So yeah. So apart from it, let's go on with FPGA, ASIC, and microcontroller. When to use when? This is the major question everyone should be thinking of. I know FPGA, I know to design an ASIC, I know to use how to program a microcontroller, but when you will be switching which devices and when industry people are using which particular devices to for their application. That is important to understand. And let's go ahead with how we can understand like how we can decide in which particular device I need to deploy my application. So as a first point, we will compare between FPGA and ASIC. Okay. So yeah, FPGA ASIC. So the very first point is time to market. Okay, time to market in sense someone gave you a problem solution like problem statement, like you were given with a problem statement, right? So in terms of ASIC, as like it follows the traditional electronic design protocol, you need to understand the behavioral description, and then you need to convert into structural, and then again you need to identify the physical components and then interconnection, everything, and then again you need to test verify, a lot of things are there. So in comparing it on FPGA you need to convert from behavioral, just you need to program your behavioral problem. You need to just program a behavioral description and it will straight away convert into a product. So that's why time to market is fast on FPGA. These things are for FPGA and this is for ASIC. Okay. So FPGAs are fast to market. And then NRE. NRE is non-returning engineering cost it is. So non-returning in sense like you design the ASIC. Okay. In ASIC you have lot of money involved. Like you need to start from the scratch and then design each and every particular part. And if it is not working at the end, you need to scratch everything and come back from the start again. So that's why non-returning engineering cost is very high. So what are the good parameters? If you want to fastly prototype one solution and put it on the market, FPGAs are better. Okay. If we wanted to have non-return engineering costs as low, then FPGAs are better. And then if in terms of design flow, as I said, like in design flow in sense, how you are going to make that particular product or particular solution, make that like deploy that particular solution. So in FPGA, as I said, you need to just define the behavioral description, and at the end, whatever connections and the physical design, it will take care of itself. I hope everyone understand how physical designs are done in the FPGA itself from this particular slide. So if you can see, you just need to write a program, and the program itself, like your whatever tool you are using. For example, you are using Intel FPGAs. The tool you are using is Quartus, and that Quartus is smart enough to understand what should be loaded in this particular LUT mask, sorry, LUT mask, and then what should be programmed, like what should be the input to this particular configurable logic block, and what should be the switching block. So everything is taken care of from the tool itself. So you don't even need to think about it. Just you need to think about how do I create an optimal behavioral description for my problem statement. If you're able to do that, everything else is taken care of. That's why if you can see from this particular slide, like change. Yeah, design flow is very simple compared to your ASIC. ASIC again, as the story goes, you need to define everything from the scratch and choose everything. Okay, and then unit cost. If you can Google any FPGAs, per unit cost is very high on FPGA, but in ASIC you would be understanding like you would be hand picking each and every component and interconnects, right? So that's why unit cost is low. And if you want to have a sorry, if you want to have a low unit cost, you would be using a yeah, you would be using a ASIC. So ASIC clicks on this particular point. If you want to go with low unit cost, you should choose an ASIC. But if you wanted to have, okay, ASIC is low unit cost. And what about the performance? Performance also high in terms of ASIC. Can anyone say why? Like, I think the answer is obvious. So as you are only building a circuit for one particular application, the performance should also be high, right? Because you are now able to run that particular program only for that particular chip, and should be like the main problem statement you would be looking is like I can get a solution, but how fast I can get a solution. So while designing itself, you would be considering that in a mind always, and that's why performance is always high in ASIC. So ASIC clicks this box as well. And apart from it, we have power consumption. Power consumption is not really high in terms of FPGAs. It should be around moderate, but it would be mostly higher than terms of ASIC. ASIC is again, if you are defining an application, everything comes into a play. Like you can understand what are the components, how much the power requirement, everything is very well defined, and you are trying to choose how much the particular component should be consuming power because you can choose a component. That's why these three boxes are clicked by ASIC, but the last, like the first four types are clicked by FPGAs, worked by FPGAs. And then apart from it, unit size, yeah, unit size is also you can reduce the area of your particular chip, right, to very compact as possible in ASIC, but in FPGA, it is already defined by your manufacturers. Let's say your manufacturers, Intel or Xilinx, they already define the size of the FPGA, and you will not be able to control that size unless you create your own FPGA. So this is also click and like this is also goes to ASIC. Okay. So this is how. So in short, ASIC is like assume your problem statement is very clear and you wanted to create a chip for that particular problem statement alone and nothing more. Even there is no future updates or nothing, you should prefer ASIC. But you want to create a chip which I need to have like very fast prototyping. Like I want to put it as soon as possible into the market. I wanted to maybe upgrade that particular solution in future. So if that is the case, you should be choosing an FPGA. Okay. So yeah. So let's now compare FPGA with microcontroller. So yeah. So if anyone can say what is microcontroller first before going on into FPGA versus microcontroller. You can tell me what is microcontrollers? Come on, guys. Microcontrollers should be pretty close to your hearts. Okay. Okay. Let me give you again. Microcontrollers are used everywhere. Even where you guys should answer. I can't answer everything. I said microcontroller are used in many places. You can look around yourself and then tell me at least some example. Designed so someone is answering designed to perform specific tasks.
It's a ASIC
So it
chip
is a microprocessor.
designed for a specific task.
Okay. Mm, okay. So what, sir?
It's a
Can you explain what
programmable
is it?
digital
Yeah.
circuit, sequential digital circuit.
Yeah. So yeah, I'll take an answer from one of our participants. Microprocessor along with peripherals fabricated in a single chip. Yeah, that makes sense. So you have a microprocessor which is running your particular program. It can be anything. That particular program is again like that particular program is on your particular microcontroller, and that particular microcontroller is responsible to run that particular program, right? So yeah, so anyone else microcontrollers can utilize with many peripherals to do a task as needed. Yeah. So yeah, microcontroller are nothing but a microprocessor along with all the peripheral attached with it. In short, right? So let us compare that with an FPGA. In terms of FPGA, you have nothing like that. You have just your configurable logic blocks with multiplexer and registers and everything. Okay. So that's what an FPGA has, but a microcontroller has a microprocessor. What does it mean is like a microprocessor have a dedicated units. If you have a little understanding of how a microprocessor is designed, it have an arithmetic logic unit. It has an memory sections. It has even what to say controllers and data parts. Lot of things are there inside a microprocessor. Apart from it, you have microcontroller has lot of things like counters, timers, interrupts like that. So yeah, if you just think in a broad scale, so FPGA is just like it can operate independently. It is not like a sequential circuit. It is independently like if you have multiple LUTs, right? In that LUTs, you can consider one particular part to work on different function and another part to work on different function. So the independence to all other logic elements is present in the FPGAs. Whereas in microcontroller, it is like as I said, like it is kind of a CPU, small CPU inside a microcontroller runs one instruction at a time. We call it as instruction, right? So it will run one instruction at a time. Apart from it, max clock speed. Yeah, max clock speed is also if you have a microcontroller which is already made, you just can't change everything. You can change some things, but it is not scalable for every what to say. Let's take an example. You bought a AVR microcontroller, let's say at Mega 2560. It comes with one particular oscillator inside the chip itself. You can either use that particular internal oscillator, which is again defined to some particular frequency, let's say 8 megahertz. And if you don't want to that particular frequency, you would be using an external oscillator. I hope oscillator is a device which can generate frequency for your microcontroller microprocessor is like that. Okay, so you can choose from very defined amount of frequencies, but in this particular FPGA you can generate your own clock inside an FPGA itself, assuming there is only one master clock. Already there is one master clock present in an FPGA. You can either increase the clock speed or you can also reduce the clock speed. So those things are possible on FPGA, whereas it is limited on microcontroller. I'm not telling it is not possible, but it is limited. Whereas in FPGA, you can create 10 clocks if you want to create for some application. Yeah, you can create it on FPGA. So that's why it is depends on the design. Whereas in microcontroller, it is not. So apart from it, what do we have? We have IOs. So IOs is also like pretty much defined on both the devices. Limited IOs typically 8 can be accessed at a time. So accessing is what differing. Like so both the of course both are chips and both are chips and have a defined area, right? So within the that particular area in sense size of the chip is what I'm telling as area of the chip. Whatever the size is, they need to accommodate everything inside that. So both of them have a limited IOs, but how you can access an IO? So in terms of in terms of my microcontroller, like at Mega 2560, it has ports and you can access one port at a time, which can contain eight input or eight output, right? Like that, right? In FPGA, you can access any as much as input as you want as parallelly. Parallelly in sense, it's like assume you are trying to read a value from a sensor. Okay, maybe let's call that particular sensor as ultrasonic sensor. In FPGA, you can read like this. Like if this is one clock cycle, I hope you can understand this particular diagrams. So in one clock cycle in FPGA, you can read like that. Like you can read the value of ultrasonic sensor one, ultrasonic sensor two at that particular time. Maybe we call it as t equal to 0. But while in microcontroller, you if you need to read the value of ultrasonic sensor, you will in one clock cycle you would be reading US1, and the next clock cycle you would be using a next particular value. Okay, this kind of things are there. Apart from it, yeah, let's continue. Okay, let's continue over here. So power usage is very dependent on FPGA based on your particular design. So it is very dependent on FPGA. And in microcontroller, it is it has a lot of modes, right? It has active sleep mode, inactive mode. So it has a lot of modes to understand that this particular device is not performing as required. You can put that particular components into sleep mode. Example, ADC can be went into a sleep mode, or it can use UART into a sleep mode, similar to that. So in terms of cost, microcontrollers are made for some specific application, like as it is a general purpose ASIC, I can say, because it is trying to run a program. So it is a FPGAs are also general purpose board, but it can be relatively costly comparing to microcontroller and FPGA boards. Okay. So yeah. So I'll give a intro on HCL, SCAD, and other tools right now. So first, we will start with HTLs maybe. Yeah. HTLs are nothing but hardware description languages. So usually what we will do in microcontroller, what we will do is like we will be using embedded C or some C program to run your microcontroller. But in terms of to program your FPGA, you need to learn like which is not really that hard. So you need to learn this particular language called hardware description language. So as the name suggests, this particular hardware description language is like you are defining like in any language, embedded C or something, you are defining a software. Basically, you are defining something which should be running on a CPU or something like that. But in terms of hardware description language, you describe as a digital circuit how your program should work as a digital circuit. So that particular definitions are written in this particular language, hardware description language. Okay. So why do we need that? So as we were speaking about electronic design, we have a lot of big designs. Based on that particular big designs, we can't put every components on hand and then test out each and individual and wire it out. Those problems are there. Instead of that, I can basically define it as an what to say define it as a program, right? If I can able to define it as a program, and what there can be one tool which can understand that he is describing this particular component, then it would make things a lot easier. That's why we were using hardware description languages. And yeah, so we have some tools which can understand that particular hardware description languages and convert the hardware. So those languages are one is VHDL, we call it as very high speed integrated circuit hardware description language, or VHDL. So this language and Verilog. So these two languages are most commonly used on many industries to do this particular electronic design and then designing, verification, lot of things. Anyone wanna? Okay, so I'll continue. So we are at least in this particular theme or EYRC, we are focused on learning about Verilog. So we will be teaching Verilog and how to design some cool components like UART, like that in UART. Now, one more spoiler is again in this year also we will be designing a CPU architecture, RISC-V. So RISC-V is an open source CPU in which many people are using in industries and to design microcontrollers how to design and RISC-V from scratch. So using Verilog, of course, and then how to test it and verify it. So those things are there. Even we would be running some programs like software in and hardware, right? So software would be some algorithm, and then hardware is your RISC-V CPU design. You would be running a software in the hardware. So those things are there. So yeah, I'll at least give you what is Verilog and what are the styles, like what are the different ways you can write Verilog code. So yeah, so Verilog, there are multiple types of coding style in Verilog. One is called structural. Here, if you can see, one is called structural. And in structural in sense, if you remember from the first one or two slides, I spoke about behavioral to structural description. In structural description, I said like choosing which components and which interconnections, right? So that is what here we are going to describe. Now I will like to take an example of full adder. And if you can see, we have one XOR, basically 1 plus 1, two XOR, two AND gate, and one OR gate. And we are defining one B should be connected to this particular XOR, and then output of this particular XOR should go here, and then I should take C in from this particular value and then create an XOR. And then we have AND gate like this, like this, like this, right? So basically, I'm designing how this particular component should be structured and connected together. So in Verilog, how do I do it is something like this. So I define what is my particular behavior of the circuit, like that. That's just a syntax and name. Whatever blue it is, and say, like keywords of this particular language. So I defined this particular module. N module means like I'm creating one particular Verilog file, okay, which is called as full adder, and it takes A, B, and C as input, and then output is C and carry out. Okay, and here I'm telling how I can use. If you can see, I have used XR as a word, and then said one name. X1 is nothing but that particular unit name, and then I'm telling how the connection is. If you can see, uh, wire one, which can be W1. Let's call this as W1. W1 is for output wire, and A is there. A is connected to this value, and B is connected to this value. Similarly, you can check out this slide later to understand how these particular values are connected and how it is described that in structural way in Verilog. So this is one way of modeling to define what should be the behavioral description of this particular code or this particular design, which is full adder. Similarly, we have some more designs or some other styling. One is data flow. So data flow, in sense, we are describing how the data are flowing or how the data are being utilized. So I hope everyone remembers what should be the digital value design in sum. So which is AX or BX or C. So I explained, like I expressed that like this, and then in carry out it should be if you know from full adder, it is nothing but two half adders, right? Two half adder plus one OR gate. So that's how, if you can see, it is implemented over here. So similarly, even if you define two half adders plus one adder, one half, like one R in structural way or very data flow way, Quartus is very intelligent, or your Verilog tools are very intelligent to understand this is nothing but a full adder. So you can also try out in our teams that how this particular software is now able to recognize other different designs. Okay. Apart from it, we have one more design, which is behavioral. In behavioral, you would be mentioning if you consider A, B, and C as input and C out and S as an output, I would say directly that if 0, 0, 0 is my input, A, B, and C in, A, B, and C in, S and C out, what should be 0, 0, right? I would define straight away that this should be the value of the for following inputs. So this is called structural, sorry, styling, behavioral styling. Okay. So apart from it, you can see there is something called netlist views in any Verilog designs. And if you, whatever, in whichever style you write in the previous, it can be behavioral, data flow, or structural. At the end, it will understand that you are trying to do a full adder and it will implement a full adder. Okay. Anyone want to ask? Should I continue? Okay, I will be continuing. So consider I was speaking about tools, right? In terms of FPGAs and Verilog. So one of the tools we would be using in the theme is Quartus Prime and then Model Sim. Quartus Prime is the synthesizer from Intel. So and then Model Sim is for simulation verification. And apart from it, we have Xilinx from Xilinx. So Xilinx and Intels are the lead manufacturers of FPGAs. Apart from it, we have what? We have a lattice semiconductor, even microchips entering into FPGA competitions, like competition of FPGA manufacturing. And then that is semiconductor, so microchip. Yeah, some more people are there who's trying to make FPGAs. And even Arduinos are trying to put embedded like FPGAs with the microcontroller. And I hope some of you might have heard Arduino MKR with our boards, so which has FPGA along with the microcontroller to do interesting stuff. So yeah, everyone is trying to explore this particular domain on FPGA to create better engineers, I hope. So yeah, so we would be speaking about applications now. So what do you guys think as an application of an FPGA? Can anyone answer? What might be an application of FPGA? What does it comes into your mind? You heard a lot of things till I said. So what do you think it what are the things comes into your mind where you can use FPGA? Can anyone put it on chat or something? GPUs, GPUs in sense. Okay, why not? Any other answer? Prototyping, ASIC, yeah, why not? Any digital circuit can be programmed into FPGA, yes, right? So yeah, so answers are coming out. So we'll start with chip design. Yeah, you can design a chip. You can visualize. Let's say what your goal is to do a digital signal processing. For that, I need to do some cool stuff, like maybe I want to process calculator. Yeah, you can do anything, but network tasking, yeah, you can do that. So yeah, I'll answer some questions. So application of FPGA, one is chip design. As I said, like you can visualize any digital logic or else any algorithm and understand what should be output. So you can prototype an electronic design problem and then create a chip out of an FPGA, like not out of FPGA. You can deploy that particular behavioral description into an FPGA and use it for chip designing and for verification. Like I'm speaking very less about verification, but industries uses FPGAs to do lot of verification. So they don't want to directly spend lot of billions into directly deploying an ASIC. Instead of that, they will have expensive FPGAs to deploy or virtualize all their functionalities of their ASIC in an FPGA first. Then only they will start designing their chip design itself. So that application comes into play. And then, as I said, CPU design is also there. CPU design is okay, muted. So apart from it, the people uses FPGA to design CPUs. Even they try to inject attacks. I hope everyone knows latest attacks on Windows, right? So similarly, people design CPU, they inject attacks like it can be any attacks, power attacks, side channel attack. There are a lot of things to speak, but I would keep it simple. So basically, FPGAs are used for designing CPU as well. It can be new CPU, you can create your own CPU or you can use FPGAs to deploy like modify the existing CPU and create a new, ISA it is called. You will learn a lot of things like that in the team, but let's stop there. Apart from it, we have of course our ML and DL inferences. So ML and DL in sense, assume you wanted to do object detection. In object detection, what you're trying to do, you're trying to run it on a CPU, GPU, or even TPUs. So these are all also little hardware capped, right? Even a CPU, GPU, and TPU is also hardware capped. But if you know this is my exact application, and I wanted to make sure that particular ML or DL algorithm, like the object detection algorithm, runs ultra fast. So if you want to do that, you can use FPGA. And of course, FPGA also some limitations called resource utilization, how much resources you can use based on your particular micro like FPGA board. You can use that much amount of resources to deploy one particular application. Okay. Apart from the robotics is not really an application of FPGA, but we are trying to teach you FPGA from robotics. So you can learn a lot of things in an exciting way. So yeah, so these were the applications. So at the last, like as an end to this particular session, we will speak about the design flow on FPGA, how we are going to design if I want to complete one particular electronic design. So let's take an example. Now my application would be mod 4 up down counter. Mod 4 up down counter is my application, or this is what someone asked me to design. So what I will try to do is, so I will understand what is the problem statement, that is the design entry, which is mod 4 and up and down counter. I will write a program. I can show you a program later, but I will write a program and to say this is like mod 4 and up down counter, I will write the behavioral description. And then in simulation, I will verify it. After writing any code in your Verilog or something, you can verify in terms of waveform level or even in terms of RTL level, whether this particular design will work or not. So behavioral verification can be done, functional verification can be done. So once you write a program, then it will synthesize if we are using Quartus tool, it will synthesize that particular program. Synthesize in sense, it will convert the algorithm into a hardware block. So that hardware block will be verified, like hardware block will not contain redundant amount of code. Assume you are using a lot of unnecessary variables. In hardware, you will not have that much space to accommodate everything. So your tool is very much smart enough to understand that you are not using those tools, like those variables or something like that. And it will like chip off basically. Basically, it will not synthesize those blocks and it will use whatever required out of that blocks. So I show in later slides. And then apart from it, we will have implementation. Implementation in sense placing, fitting, and then connecting. Place and fitter is there, and then interconnection should be made, and then LUT mask should also be programmed, right? So those things are also done using implementation. And then there can be like we can verify timing based verifications as well. So if you wanted to happen, like if you wanted to express one particular function within this particular time, you can check whether you can do that. Okay. So yeah, at the end you can program the FPGA using bit streams. So we will be going on through that very fast. So yeah. So the very first thing is to convert the HCL model into circuit of basic logic domains, which is called synthesizers as well. And then apart from it, there is something called technology mapping. In technology mapping, what it is like, we have different FPGAs in the market, right? So one particular synthesize after synthesize, you have some amount of defined blocks, like these blocks are required. But how will you map that particular blocks into your configurable logic block? How will you do it? So those is called that is called technology mapping. And then there is in each target platform they use different tech library. We call it as tech library in FPGA world. And then that particular library will handle how to map that particular synthesized block into actual FPGA to complete interconnection and everything. Okay. So at the end, yeah, that's what I'm speaking about. Where exactly should be placed on FPGA? Like in FPGA itself has a lot of configurable logic blocks. It can be some 10,000. It starts from some thousand and it extends till some lakhs. Okay. Based on the cost of the FPGA, you will get a lot of configurable logic blocks to program. So yeah, so these are the steps. And then at the end, you can use the bitstream. Like bitstream is similar to your, like, at least in terms of comparison between microcontroller, you can consider machine code is there, right? Machine code is nothing but your program. And here bitstreams are nothing but your configuration elements to run your program. Okay, so as I was telling you, let's consider mod 4 counter as my device or mod 4 counter as my application. So this is the, I hope someone can identify which particular modeling style I have been using here. Can anyone? It is behavioral. Okay, so if someone can't, it is behavioral. I am defining what should be the value for the given input. Here, positive edge of the clock means this is nothing but we call it a sensitivity listen very low. Positive edge of the clock in here means like every positive edge of the clock, like we have a clock like this, right? And this is nothing but positive edge. At every positive edge, I'm going to trigger this particular block. And this block will do what it is supposed to do. So assume mod up is already initialized with 0. 0 plus 1, what it is? 1. Similarly, mod down, what it is? 0, and it is what? Minus 1. So 0 minus 1, if you do, basically it is minus 1. In Verilog, if you do 2-bit 2's complement, it will have that particular value. Okay. So similar thing. Yeah. So one more thing here to notice, in any program, usually these things happen serially, right? So at one clock cycle, it might do this particular operation. At second clock cycle, it might do this particular operation. But in Verilog, it is not like that. It will execute parallelly. If you can see, this is nothing but non-blocking assignment in Verilog. And this is to indicate that this two particular like update in this particular register should happen at simultaneously. So it should also be done in clock one. This should also be done in that clock one. So that's how you can also control the level of parallelism you want. I don't want, like, assume I wanted to do sequentially, you can control, like you can define that as blocking assignment, and then you can control that I want to do sequentially. Sequentially, in sense, it can happen on single clock cycle as well. It can happen on multiple clock cycle as well. You can define these kind of behavior yourself. So this is the program, and this is for mod up and down. So basically, it mod 4 counter, so it will count from 0, 1, 2, 3, and 3, 2, 1, 0. Right. So yeah, if you synthesize this particular HDL, it will give you some this kind of image. This is nothing but a RTL image. RTL is register transfer level image, like register transfer level that is called as, and it will tell like how individual register values are transferred from one block to another block to finally give you an output. So we have a clock, we have one latch, D latch or D flip flop, you can call it as, and then we have adder over here and here to complete these operations. So based on your complexity of this design, your register transfer level block size also increases tremendously. So you can explore all these things in our theme. So for now, I'm continuing. So yeah, so we did one functional simulation after writing this code. If you can see in mod up counter, it starts from 0, 1, 2, 3, and then it loops back itself. And then similarly, if you can see from this particular clock cycle, mod down is doing 3, 2, 1, 0, and it is continuing, right? So yeah, so this is functional simulation of this particular application. And then let's move to technology map. Okay. So in technology map, first thing is like, so it will identify each input and outputs. If you can see, a clock is an input, and each input and output will have a buffer. I hope everyone knows what is buffer is used for. In short, buffers are used to make sure you have an device which has input impedance, and you want to make sure that your logic level satisfies that particular impedance, then you use a buffer, right? Okay. Apart from it, it also, if you can see here, mod 0 is there, mod down 0, and mod down 1 is there, and mod up 1 is there, mod down 0 is not there, right? Why it is not there? Mod up of 0 is not there, and it took value from mod down of 0 itself. Why? If you know, so if you do 3 2 1 0 or 0 1 2 3, your lower bit remains constant for both the cases. This is sorry, one mistake. So the lower bit actually remains constant in both the cases. So that's why it is not like it neglected one lower bit over here. You can write the values in 0 0 0 1 in binary basically. So this is 3. So it started with 3, right? Here 3 2 1 and then 0. Right. So if you can see, the lower bit over here and here would be same. So that's why it was able to neglect the value of mod up of 0, and it used mod down of 0 to use it on the like logic elements. That's how your quarters or any Verilog synthesizers are smart enough to understand that you are not using this particular element like that. Okay. So yeah. So this is nothing but a chip planner. So this particular diagram is from chip planner. Chip planner is nothing but you have your entire FPGA. Basically, this is an entire FPGA block, and you have lot of logic elements, right? So you have those small elements. Each FPGA has defined amount of logic elements. Example, D0 Nano has 22,320 logic elements. It is shown like similarly. Any FPGA will have defined amount of logic elements. And if you can see, there is some gray shade, like little shaded areas there, right? This means like this much amount of logic elements I'm using. Like this particular block I'm using. Like this is nothing but blocks, like small blocks, squares are there, rectangles are there, right? These are blocks, and within this particular block there are totally 16 configurable logic blocks. So each particular thing will have 16 configurable logic blocks, and each small rectangle will have 16 logical blocks, but you may or may not use that much amount of logical elements. So if you can see here, I am using 1, 2, and 3 logic elements. Within that, I will show you how the LUTs, like lookup tables and configurable logic block, is exactly how it look like. But apart from it, if you can see from this diagram, we have something else. Like we have this particular yellow line. These are embedded memory bits, and then white fabric we have, which are programmable switches. Apart from it, we have some memory spaces. Right. Apart from it, this brown color values, like these things are IO pads, and with IO pads are always with the IO buffers as well. So these things are there. Yeah. So yeah, if we have a close look at, like, if you can see, this particular small logic block has this much amount of logic elements, and this particular logic element inside this particular, maybe this particular logic element, we have this particular LUT, and then as I said, like one configure logic block has an LUT, one register, and a multiplexes, right? So this particular logic block has a so takes a four. This is four input LUT. We call it as four input LUT. It can vary in number based on design of an actual FPGA, like an manufacturer basically. So this four input LUT will have LUT mux and everything. This is that LUT. Those are defined inside it. And then as an output, it gives combinational output, some amount of some combinational circuit output. And then this can be passed to either one more logical, like one more CLB or some other CLB. If you can see in previous slide, it had a lot of CLB, right? Lot of CLB. This can be passed to somewhere here, or this can be passed to an adjustant like that. Okay. So here, just a minute. Yeah, here it is kind of passed to one more configurable logic block, or else it also can be using the register and stored on the register from this particular multiplexer. So it depends, and then it can also pass this particular combinational value to some other some other, like two or more configurable logic blocks, or else it also can take input from some other logic element as well. So this is how each configurable logic block is defined in terms of each FPGA internally basically. So yeah, so I think by this end, this particular text session is getting concluded. So if you have any questions in terms of in this particular session or in terms of registering in the Yantra robotics competition, you can ask. Yeah, you can also check the chat. We have shared one link. You can check what is the theme introduction for different themes. Maybe I can show it on my tab as well. So this is our portal for this year e-Yantra robotics competition registration. And of course, we have this final day. Like today is the last date for. I think this is the last date for early bird discount. Okay. For some reason, I can't. I hope my screen is visible. So yeah. So this is our portal, and we have today is the last date for early bird discount as well. So you can see if your college is applicable for ELSI and then check out how much discount you can get. If it is not available, like if your college is not ELSI, you can ask your teachers to make sure your college is ELSI. You can register from this particular button and fill small little details over here. And I think I have a discount referral code or something. Maybe I can give you one referral code. Referral code. What is the referral code? Yeah, you can. You have referral code. Yeah. We'll give you one referral code if you want extra discount. Yeah, apart from it, you can go to this particular page's themes, in which you can see what are the technology stack used by some other themes and what are the implementation, like what they are trying to do. For example, this logistic cobot uses ROS2 as technology stack, like main thing. Apart from it, you have move it and everything. Apart from it, you would be using real manipulator in our IIT Bombay, Yantra, to work on that particular robot. Like you can use that particular robot controlled remotely. So those things are there. Apart from it, we have balancing build based on control system and a particular give you please explain the recommended bot thing. Yeah, I'll give I'll explain. Before that, I will say if you are selected to stage, we will be giving you hardware. Like for most of the teams, apart from this logistic cobot, if you are selected for logistic cobot, you would be we would be giving you remote hardware access, which is real like industry standard UR5 ARM. Okay. So yeah, I will now explain what is recommended bot thing. So yeah, if you see from the diagram, I hope my screen is visible. So yeah, if you see from my diagram, Eco bot is like it is deployed in an industry. Okay, in that industry, it is trying to check if that particular machines are following industry standard or sustainability standards. And if it is not following sustainability standards, this bot should navigate or resolve that particular problem. In terms of learning, I would say what you will be learning. Of course, if you are new for FPGA, you would be learning about what is FPGAs and then how to program an FPGA using Verilog, and those things you will learn. And if you want to learn CPU architecture, that also you can do. So if you want to learn CPU architecture, we are teaching RISC-V CPU implementation from scratch. And then serial communication instance, you would be learning how to implement UART transmitter and receiver using a Bluetooth module to communicate between yours, like your bot and then what to say, your bot and we call it as eco center. You can to communicate between two devices basically. Apart from it, you will understand how exactly FPGA helps in utilizing the parallel processing capabilities that it offers. So those things you can learn. Yeah, as I said, like this is simulator plus hardware. In stage one, you would be implementing everything that will be used for stage two of the competition in simulation in stage one, but in hardware in stage two. So it would be pretty nice, like pretty fun way to explore around FPGA, learn little time getting frustrated. Everything is there. So any more questions? So yeah, we have your referral code at the chat as well. You can use that referral code to have extra 10% benefits. Which stream is difficult for a beginner? Can I leave? You can wait for some time. So which stream is difficult for a beginner? Yeah, how do I say? It depends on your interest. Anything will not be difficult if you are interested enough. Anything will not be difficult enough if you are interested enough. If you wanted to work on, like, everything we are teaching is like very important for you to understand, like work on your future projects. You can use whatever you are trying to learn over here in your future projects, and that is like very boost for your career itself, like, yeah. So if there are no more questions, of course we can wind up. If someone has any other questions? Okay. Okay, then thanks for joining, and hopefully you can see me in our team. Thank you all. Thanks for joining.